Hey guys, I'd like to talk to you about some Enolate chemistry. And some reactions in Enolate chemistry are aldol reactions, mixed aldol reactions, aldol condensations, and intermolecular aldol reactions. And I'd like to give you some practice today and some review as well. So to start off, we have aldol reactions. And here we have what is an aldehyde. And to perform an aldol reaction, you need to turn it into an enol and have it react with another aldehyde. So let's show how it happens. So NaOET separates into OET minus and Na plus. OET minus grabs an alpha hydrogen, which is the hydrogen next to the carbonyl carbon. The electrons from that bond form a double bond, which causes the electrons in the carbonyl bond to form upwards to an O minus. And it forms something like this. And this can react with another aldehyde, like I mentioned. And it doesn't need to be an aldehyde. It can be a ketone as well, as long as there's hydrogens on the alpha carbon. So the electrons on the O negative go down, forms a double bond. The double bond goes out and reacts with the carbonyl carbon, and then it goes upwards to make the oxygen negative. And it looks like this. And the O negative here can react with an H to form OH. And it can be kind of complicated, so you should definitely number your carbon chains in order to make sure everything is connected in the same place. And you can see here that it is 1, 2, 3, 4. The 2 here reacts with the 1 here, which is 1, and it's connected to 2, 3, and 4. And it can actually form another reaction to take off the OH. And it can only be done in heat because OH is a poor leaving group. And the way it's done is that another alpha carbon or an alpha hydrogen is pulled off by an OET minus, forms a double bond, and it causes the OH to fall off. And it looks something like this. And next, let's move on to mixed aldol reactions. When there's two aldols, one is turned into an aldol, and the other one is reacted with as a ketone or an aldehyde. And you can tell which one it is here because there's an alpha hydrogen here, and there's no alpha hydrogen here because it's a benzene. So the OET minus reacts with the hydrogen, goes up, the double bond goes onto the oxygen, and it looks like this. And then it goes down and reacts with the other aldehyde. And then it causes the carbon or the double bond electrons to go into the oxygen. Looks like this. And then the oxygen reacts with an H because it's negative. And something interesting about this is that there's a lot of pi bonds, and that means it's pi conjugated, which means that the OH can leave even if there's no heat because it's more stable that way. So an OET minus grabs an H, forms a double bond when the electrons collapse down, and then the OH leaves. Looks like this. And while we have some practice, there's another way to make sure that it reacts in the same way you want. Here, there's 3 possible ways if there was no LDA, for it to react. But when it's an LDA, it forces it into a certain product. So the LDA would pull off the hydrogen at the less substituted side, and that's because LDA is bulky, and it would turn into an enolate like this. And then it can react with the other one. And why don't you try it out? Okay, so it would look something like this. It would go out and react with the other carbonyl carbon. The electrons go onto the oxygen, and it's like this. Then it goes out and reacts with an H. And what would it look like if it reacted with heat as well? The H here would be pulled off by an OET minus. And the double bond gets formed due to the electrons collapsing down, and that forces the OH to leave. Now let's do some more practice. Okay, so the O here, it's symmetrical, so it doesn't matter which side it gets pulled off. I'll choose the right side, OET minus, grabs an H, the double bond is formed by the electrons being collapsing, and then the double bond here goes onto the O, and looks like this after. The O negative electrons would collapse down, and then the double bond would go out to react with another ketone. And then the double bond would go onto the oxygen. It looks like this. And then the O negative would react with an H. From an HOET. And then if you were to do a condensation with heat, such as this, the OET minus would grab another hydrogen and it would go down, force the OH to go off. And now let's look at some electromolecular condensations. Here, if it were to react with NaOET, HOET, there would be 3 alpha hydrogens, one here, and one here. This is a terbutyl, so there's no room for hydrogen. And you know which hydrogen to pull off to form the original enolate because 5 and 6 member rings are favored. And now you just need to count to see how many carbons would go into the ring and then go from there. So if you were to start here, be 1, 2, 3, 4, 5. And then if we were to start from here, it'd be 1, 2, 3. And if you were to start here, be 1, 2, 3 as well. Which means that this this hydrogen is most likely to be pulled off. And when it's pulled off by an OET minus to form the enolate, it collapses, make a double bond. The double bond goes onto oxygen. It looks like this. And then it reacts the same way as before. The electrons on the oxygen would collapse down, causing the double bond to go out and react with the carbonyl carbon, causing the double bond on that to go onto the oxygen. And what's important here is numbering and knowing how big the ring is. So it starts here, 1, 2, 3, 4, 5. That means there is a 5-membered ring in the middle. On 1, there's nothing, and it's connected to 2, which has a double bond. It's connected to 3, or 1, 2, 3. 3 has nothing. 3 is connected to 4, which has nothing. It's connected to 5, which has an O negative and a tert butyl. And the O negative would react with an H in order to form an OH. And then, since it's already a ring, it's very likely for an OET minus, or just any base, to react with an H at the alpha carbon in order for it to form a double bond to force the OH to go off. And then it looks like this. And then why don't you try and practice with this one as well? Okay, so here you see all the places where you can add an H at the alpha carbons, and then count how many rings or how many carbons would be in the ring if it were to get pulled off. So here it'd be 1, 2, 3, 4, 5, 6. If it were to be this one, it would be 1, 2, 3, 4. And then if it were to be this one, it'd be 1, 2, 3, 4. And so we have a winner. So an OET would grab the H, the double bond would be formed by the electrons collapsing, and then the double bond on the O would go onto the oxygen. And it would look like this. And then the electrons on the oxygen would collapse down, and the double bond would react at the other carbonyl carbon, causing those electrons to collapse upwards onto the oxygen. And this is where numbering, again, is important. 1, 2, 3, 4, 5, 6. So draw your 6-membered ring, and again, go around to see which goes where. So 1 is connected to 6, which has a double bond on it, or an O negative. And it's connected to a 5, which has nothing, next to 4, and it forms a pentagon with 3. And 3 here is connected to 2, which has a double bonded oxygen. Then the O negative would react with an H. It would look like this. And then again, because it's already a ring, it's very likely for an OT minus to grab an H that's at the alpha carbon to form a double bond, which forces the OH to go off. And it looks like this. And that's the end of my video. I hope you enjoyed it.